In this lecture, we will talk about Liouville's theorem. It tells us how the density in a phase space changes with time, with very important consequences in the statistical mechanics. So we look at phase space. Let's say we have a simple 1D system for which we have one generalized coordinate and one generalized momentum. And in this phase space, the yellow lines show the trajectory along which a particle moves. Okay. Now we consider an ensemble of particles, many particles, and they of course occupy, they have to be placed along the trajectory. After all, in a phase space, the particles move along their phase space trajectory, so it must be somewhere on the trajectory. So they must be on these yellow lines, okay, one or other. Of course, we can choose a very large number of particles, a true ensemble in a statistical sense, and nearly all lines will be kind of filled, the dots everywhere. And if we do not draw the lines, then if we just look at the points, it will look like a swarm of particles, many particles, and each one is moving. Some are going down, some are going towards the right, and let's say in this box some particles are going out. So as such, if we look at grid by grid, then this swarm of particles in the phase space, they are constantly moving from one grid to another, and they are always in motion. Now, to analyze this swarm, a useful quantity, it can be defined as phase space density, rho, which is a function of q, p, and t. So that means we are defining the density for a specific value of q and p. So what we do is essentially we look at how many how many points are there in the vicinity of this q and p, count them up and divide it by the total number in the swarm, and that gives us a kind of a probabilistic representation. We call it density. So density of the phase space rho multiplied to the total number of particle will give us how many points likely to be found around a given q and p. The question that we ask is how rho change with time. I mean, how does it change with time? So to understand that, I mean, we can just consider a simple 1D flow like a charge current that we have seen earlier. Let's say we have a tube-like structure with charges flowing along it, and then we already know if the charge density is rho and the velocity is v, the number of charges passing across a line per unit time would be simply given by charge density times the velocity. So this current density, as we defined, it's very useful quantity to predict that, or rather it's a useful quantity to understand that how a system is flowing. For example, in the case of a three-dimensional flow, we will have the density multiplied to various components of velocity, vx, vy, and vz. And this can of course be represented instead of using the unit vectors, we can simply use the tuples rho vx, rho vy, and rho vz. And for a 2n dimensional phase space, the rho will be multiplied to q1 dot, q2 dot, then q1 dot, qn dot, and all the p's. This current density, it could be easily used for calculating the flux. So for example, in phase space, we consider a volume G. and we would like to know that how many phase points are leaving this volume. Just like we discussed before, that phase points are constantly in motion. They are moving from one grid point to another. They are of course following the trajectory, and following the trajectory they move from one place to another. So as such, in a given volume G, if there are points inside, they would definitely go out following the trajectories again, and one can calculate easily how many points are leaving the volume by calculating flux, which is a surface integral of the current density over the surface, of course, surface of G. And this flux must be equal to the rate of change of whatever quantity is contained, in our case total number of points inside, which can easily be estimated by taking the volume integral of density. So density and the volume integral of G gives us total number of points inside, and its rate of change must be equal to flux, albeit with a negative sign, because if J is positive, the particles are going out, then the total number of points inside G must go down, and the negative sign accounts for that. A big assumption in writing this is the phase points can't be created or destroyed. So the phase points, they follow a trajectory, and this trajectory has no beginning or end. I mean, as such, so in a given volume, the particle must have entered this G through some by some trajectory, and then it will leave G at a later time using the same trajectory. So a trajectory can't start inside. So this is why the conservation of points leads us to the following principle, that flux must be equal to rate of change of whatever we have inside, with negative sign, of course. Now, the left hand side, the surface integral of J can easily be converted to a volume integral using divergence theorem. So we have the surface integral of J, and that becomes the volume integral of the divergence of J, and we bring the right hand side where rho is the only time dependent quantity, so we can push the partial derivative inside, and eventually we have the volume integral of divergence of J plus del rho del T. Now this holds for an arbitrary volume G, so which means this would be 0 only if the integrand vanishes. So that gives us a continuity equation, that rate of change of rho explicit dependence on time, that is given by negative divergence of J, and it follows from the conservation of total number of ensemble member. Like we said, I mean, a trajectory does not start or end, it is there, and so if we started with n number of points, we will always have that n number. Now this divergence theorem can be easily recursed in an useful form. First of all, this del operator, we look at it, it is equivalent to the partial derivative with respect to each generalized coordinate and momentum. So q1 to qn and then p1 to pn. As such, this divergence can be written as del del qj of rho qj dot, and then del del pj of rho pj dot. Now we must remember that there is a sum over j. We are using the summation convention, repeated indexes. In this case, j means there is a sum over j, and the sum is from 1 to n, of course. Now carrying out the partial derivative, we have del rho del qj times the velocity qj dot, and similarly we have rho del qj dot del qj, and corresponding terms coming from the momentum. Next, what we do is we look at Hamilton's equation. Of course, all points in the phase space, they satisfy Hamilton's equations. So qj dot is del H del Pj, and Pj dot is negative of del H del Qj. We substitute that in this equation everywhere, and when we do that, we see the last term cancels. The product of rho with this partial derivative of Qj dot and Pj dot, it cancels identically, and then the remaining term can be rearranged easily, and it gives us the Poisson bracket between density and Hamiltonian. So a very important result. So we see the divergence of J being the density multiplied to the generalized velocity vector Qj dots and Pj dots, and that gives us, if for a phase space where the Hamilton's equations hold, we have Poisson bracket between rho and H. So our continuity equation now takes the form that del rho del T plus the Poisson bracket of rho and H, their sum is 0. But this is equal to the total time derivative of rho. I mean, we have seen this relation for any dynamical quantity must satisfy this relation that we have seen earlier. So as such, the left hand side, which results from the continuity theorem, is known as Liouville's theorem, which also says the total rate of change of density vanishes. So which means that if you have a phase space and you have defined density at a particular point, you have many particles and they are all moving around, then at a given point Q and P, if you calculate the rate of change of density, the total time derivative, then it vanishes. And you see, I mean, how do you choose such points? I mean, typically if you have a statistical ensemble, you choose the ensemble members in certain way. That means at low energy you put more particle, at high energy you put less particle. And for equilibrium distribution in statistical mechanics, at a given temperature you have certain distribution. We call it Gibbsian distribution, where the higher energy, their probability of finding a particle at a given energy exponentially decreases as you increase the energy. But in any case, I mean, the specific details are not important. What is important is, suppose you choose with a number of system. Then for that number of system, this Liouville's theorem always holds, irrespective of how you have chosen the system. It could be equilibrium distribution or non-equilibrium distribution. But suppose you have chosen some equilibrium distribution. Now, what is meant by equilibrium? Well, by equilibrium we mean that we are considering many replica of dynamical system. Many in the sense statistically very many, like Avogadro number or so, big numbers. We have chosen so many systems and they are occupying the phase space. If they do, then in equilibrium you do not expect the density to be changing. So if we look at the phase space of a system at any given time and then close our eyes and look back at a later time, we should not be able to tell any difference whether things are changing. If they do, then it's not equilibrium anymore. So for such cases, the explicit dependence of the density on time should vanish, and which means the Poisson bracket between rho and H must be 0. So that means rho could be a polynomial of H, and that is a valid thing to have. I mean, that must be satisfied in equilibrium. Now, can we have an example? Say, for example, we can think about gas particles. The gas particles, we have very high velocity, we have very low velocity, and suppose we take all such gas particles. So we have a box full of gas particles and we try to describe each of them in a phase space. So in a phase space, we look at the first particle, we look at what kind of position and velocity it has, what are the q's and p's, and we put one dot in our 2n dimensional space. Then we take the second particle and put another dot. This is how we construct the phase space of all these particles. Now these gas molecules, this box of gas, it does not have to be in equilibrium. It could be in a non-equilibrium situation where there might be a temperature gradient. The lower side of the box has more temperature, upper side has less temperature, or the physical density, not phase space density, the physical density might be changing. Either way, you put all the dots in the phase space of this box of gas, and then in phase space, if you try to understand how density is changing, this is your equation. It always holds. So this is a very useful quantity, useful relation. We shall see more of this in the statistical mechanics later. There is another way one defines Liouville's. After all, the Liouville's theorem says the total rate of change of density is 0. Now suppose for a 1D system P and Q, and we are considering a small volume, in this case area of course, around some P and Q, and we have many particles there. Using these particles we can define a density. So we are defining or calculating the density by counting all the points which are there in this enclosed area and dividing it by this area. Now, as a function of time, all these points move along their trajectory. So the shape of these points at a later time might be different. And the area, enclosed area, on the left hand side we call it gamma 1, on the right hand side gamma 2, these could be different. But no, they can't be different, they are equal. That is the statement of d rho dt. How so? Well, the phase space trajectories, they don't cross each other, okay? Simply because if they do, then the problem will not be deterministic anymore, okay? So for a given Hamiltonian, we have Hamilton's equation, and these Hamilton equations, they give us unit trajectory for given initial condition. So in any case, for this area, gamma 1, consider all the points which are at the boundary. We consider that we have many points at the boundary, nearly no gap between the points. Now, how would they move? Each points move without touching another one, and they eventually get this different shape. The particles which were inside, can they go out? Of course not. When they try to do that, they have to cross path with the ones at the boundary, which is not allowed. Okay. By that same argument, the points which were outside, which we have not drawn, they can't come in without crossing the boundary. At the boundary is completely filled by all these points. So the particles cannot go out, the particles can't come in, and of course the particles which are at the boundary, their total number would also be same. So as such, the total number is not changing. If that happens, then this area containing a given number of phase point must be same at a later time. Its shape might change, but the area must remain same, because that is also another way of defining the density, the number divided by the area. We can do that. So this is another way of saying Liouville's theorem. Both are completely identical, of course, but the first definition comes in handy when we look at the statistical mechanics.